Hello and welcome to this manufacturing process technology part 2 module 20. We had learned in the last module about the various overvoltage potentials that are needed to be crossed in order for the ions to cross over the different layers like the double layer and which essentially includes the diffuse and the Helmholtz layer, and then also the ion gradients which are established by virtue of the electrochemical machining processes or the electrochemistry between the electrode and the solution. So, once we have learnt about how to do this correction in order to predict the actual material removal rate, the actual way that a surface behaves with respect to a tooling is of critical importance, and for this we are going to now cover another area which is also known as the kinematics and the dynamics of the ECM process. So, let us suppose that in this particular figure we are showing that there is an ECM operation taking place where the tool is the negative electrode, the cathode, the workpiece made the positive electrode, and we are further assuming that the electrolyte flows with a velocity v typically in the x direction. This is the x direction, and it flows between the space which has which comes between the tool and workpiece as the machining gap, and further we assume that the workpiece is having a distance y as a function of time t with respect to the tool surface, and this y keeps on increasing or decreasing based on two factors. One is how the workpiece is receding with respect to the tool because of dissolution processes, and the other is how the workpiece is being fed into the tool. So, these two are the determining factors to find out how the surface recedes away and how the tool gap gets created because of that. Okay. So, the upper electrode is being fed with constant velocity f in this particular case. So, let us say this is f, okay, in the minus y direction normal to the electrode surface, and the problem is considered right now as a one dimensional simplified problem. The instantaneous distance of the work from the tool surface is taken as y. So, let us first estimate at what rate this surface will dissolve away, which will result in some kind of a change in the distance between the tool surface and the workpiece surface. So, if we consider the workpiece to be of pure metal, the material removal rate of the workpiece is given by this formulation here. We have detailed the derivation of this earlier in the earlier modules, A I by rho z f, where A is the atomic weight and I is the current, rate of change of flow or rate of flow of charge within the electrolyte. Rho is the density of the workpiece, Z is the valency at which the dissolution is supposed to take place, F is the Faraday constant, which is 96,500 coulomb of charge. If we assume delta V to be the over voltage in this particular case, the density of the current flow therefore through the electrolyte would be given by the expression J equal to K times of V minus delta V by Y. Okay. J is the current density, current per unit area, and K is the conductivity of the electrolyte. So, how this arrives at is by a simple formulation V equal to I R. So, you already know that I is basically the current, V voltage, and the electrolyte does obey the Ohm's law. So, this becomes equal to the resistivity rho times of L over A, where L is the distance across which the current flow would take place and A is the area of cross section perpendicular to the direction of the current flow. In this particular case, the current is flowing, as you know, between the work and the tool in the direction perpendicular to the work and tool. So, obviously, the distance y here becomes the distance L, which is the length of flow of the charges, and A is the cross sectional area, assuming that we have flat surfaces of the tool and workpiece, and the area is equal in nature. So, we get the total resistance of the electrolyte as rho L over A. So, in other words, what we are trying to find out here is that if I had the current density J to be defined as I by A, or current per unit area, this is the J value, this should be equal to 1 by rho times of V by L, okay, So, in other words, what we actually get is that J is nothing but 1 by resistivity is the conductivity K, and this voltage available is V minus delta V, because delta V is the over voltage potential, and obviously length is the distance y at an instance of time t, as I have told you here. So, that instance of time the total current density comes out by this formulation which has been given here. Okay. So, once we have attempted this, we actually are able to predict the ion migration rate, just because the J is actually an indicator of how fast the ions would move and at what rate the ions would move, so that the workpiece starts dissolving away. So, now the removal of the work material causes the surface of the workpiece to recede in the y direction with respect to the original surface with velocity given by q dash, where q dash is the volume rate of workpiece metal removal per unit area of the workpiece surface. Thus, the rate of change of this gap between both electrodes is given by, again, the expression, let us say dy by dt equal to the rate at which dissolution would happen, which increases the gap. So, we write this as A I over A. Obviously, the rate has to be per unit distance. So, therefore, you divide the volume rate of removal with respect to the area, okay, divided by the area, which gives you the way at the amount of distance per unit time that the surface is going to recede because of the volume rate of removal q. Okay. So, in this case the volume rate is basically A I by A divided by rho z f. You already know that q was earlier derived as A I by rho z f. So, essentially we are looking at q per unit A, or the way at which the surface is receding because of dissolution. Okay. So, dy by dt dissolution. Okay. So, this becomes equal to one component, and obviously I think I had mentioned earlier that the workpiece also is moving by a distance f towards the tool in the other direction, in the negative y direction. So, I should reduce that or minus that f per unit time with respect to the dy by dt dissolution which has been formulated. Okay. So, this we can record as A j by rho z f, which is the dy by dt dissolution, okay, minus of f. So, that is how dy by dt is constituted. So, this equation becomes equal to dy by dt equals k a times of v minus delta v divided by rho z f divided by y minus f. Obviously, because from the earlier illustration you find that the J current density has been earlier predicted as k times of V minus delta V by y. So, we are just substituting the value of J in this expression here to find out the net value of dy by dt. So, this is how you arrive at an expression for the rate of change of gap between the tool workpiece in ECM or electrochemistry. Therefore, dy by dt can be recorded as some constant lambda divided by y minus f. Obviously, all these functions, if we do not really change the voltage too much and not certainly not all the electrodes and the electrolyte combination, they are more or less similar to each other. So, this is actually a factor lambda constant for same electrode electrolyte combination operating at a given voltage. So, this becomes then equal to lambda by y minus f, and this is the basic equation that represents the dynamics of the whole ECM process. We will now try to evaluate some specific cases based on how this would vary for different conditions of operation or parameters of operation in a ECM process. So, let us investigate the first case, which is actually we would define as the 0 feed case. So, this is an illustration where the tool and the workpiece, as I had shown you earlier, let us say this is the workpiece, it is moving with a velocity f, okay, and this is the tool. So, these are connected respectively to the positive and the negative terminal, and this is the x, this is the y direction, this is of course the x direction, and there is some kind of a electrolyte flow at velocity, electrolyte flow velocity v in the x direction. So, having said that, now if we assume the f equal to 0 and the reason, the only reason for changing of this gap y is the dy by dt dissolution, or just because of dissolution the gap is changing. So, in that event obviously dy by dt would be equal to lambda by y as f is 0, and if I were to solve this equation, y becomes equal to y 0 square plus twice lambda t, where y 0 was the initial gap. In other words, you can think of it that at time t equal to 0, y was equal to y 0, and the way that y would evolve is going to be a function of y 0 and it is going to be function of t, right. So, y is basically equal to the under root of y 0 square plus twice lambda t. So, if we further wanted to sort of plot this, so you can say that the gap increases with time, obeying the relation, the 0 feed case as y equal to root of square of y 0 plus twice lambda t. So, in other words, this is what the y 0 is. If you plot y versus t, y is on the y axis, t is on the x axis. So, obviously, it is going to be a parabola about the x axis. In this particular case, the corresponding value of y happens to be at t equal to 0, and this is a sort of imaginary projection which is not really necessary. So, that is how the gap keeps on changing. In other words, we can say that it is going to be an ever increasing gap up till the dissolution becomes insignificant. In other words, we can say that the the gap in this particular case is going to keep on increasing until the dissolution rate is affected by the wide distance between the tool and the workpiece. So, eventually this would kind of stabilize, and that would be the maximum value of y which would be attainable for after a long duration of time has passed in this particular case. Let us look at the other case, case 2, which is that of the constant feed rate. So, for all practical limitations of the ECM process, an ever increasing inter-electrode gap is not desirable in an ECM process. And as you saw in the last case, till and until the time is infinitely large, the gap keeps on almost getting in, keeps on increasing, even though with a small amount, but at some particular value probably the field drops down and it is not enough to sort of start or keep dissolving the electrolyte, the electrode, and that is probably a point of time where you can say that there is a constancy by and large of the gap. Okay. So, but then that is a large gap, and so typically this is not really a very desirable issue that the gap keeps on increasing or is very large after a certain time t has passed on, and therefore, in real practice the electrode is provided with a constant feed velocity. Of suitable magnitude. Therefore, f is a constant. So, you can say that at equilibrium the feed rate f may equal to the rate of dissolution. In other words, as you saw before, that there is a dy by dt dissolution that may be equal to the feed rate, and in that event the Ig, the inter-electrode, IEG, the inter-electrode gap remains constant. So, mathematically let us examine what this condition is corresponding to. So, we are talking about a case where dy by dt overall equals 0, in other words lambda by ye, which we also know as the distance y at equilibrium, also known as ye minus f is equal to 0, or in other words the ye becomes equal to lambda by f. Okay. So, let us now sort of change gears a little bit and try to see how to make this scale independent. This equation, we want to make this maybe non-dimensional or scale independent, because typically the IEG, the inter-electrode gap is very small, and if you were to computationally try to do something by predicting the various values here of the equations that are given here, there is a possibility that there may be a numerical term which may dominate and spoil the whole rhyme of the rhythm of the process, you know, of estimation. So, therefore, it is important that we get a scale factor, a particular minimum direction here, and then sort of try to solve everything in terms of a ratio. Okay. So, here also we are doing this. So, let us now use two non-dimensional variables which we can call as y dash and t dash, such that we can write y dash to be a ratio of the actual gap per unit the equilibrium gap magnitude y e. So, we are factoring in the smallness of the y e at somehow in this particular level if we operate through these ratios, and just see that with respect to all these in two picture how the ratio varies, you know, as a function of time ratio. And so, and then there is a time ratio which is actually equal to t divided by y e by f. Okay. So, this is an indication of how soon the equilibrium the gap closes because of a feed rate of the electrode f which is being applied. Okay. So, if I wanted to just use the earlier equation y equal to lambda by f, I could actually write this further as f square t by lambda. So, these are the two variables, non-dimensional variables, which we will try to substitute back into this equation and try to see what happens. So, we have now on one side dy dash by dt dash, okay, which is actually equal to you know that y dash is given by f y by lambda, and t dash obviously is given by f square t by lambda. Just wanted to execute this in the last step here. Y e again, if you put, would come out to be y divided by lambda by f, okay, or y f by lambda. So, obviously the dy dash by dt dash would then be equal to f by lambda times of dy divided by f square by lambda times of dt, which is actually 1 by lambda dy by dt. I am sorry, 1 by f dy by dt. So, that is how we represent dy dash by dt dash. And if I wanted to just further substitute the value of dy by dt from the last step, which was lambda by y minus f, if you may recall from the last equation, the equation of dynamics of the ECM process, I would like to arrange this a little bit. I will write this as 1 by f y over lambda minus of 1. In other words, this can be written as 1 by y dash minus 1. So, we can actually try to solve this equation, dy dash by dt dash equals 1 by y dash minus 1. So, as we recall, this would be 1 minus y dash by y dash, and if I wanted to just apply some partial fraction knowledge in order to solve this equation right here, we can arrive at y dash by 1 minus y dash times of dy dash equals dt dash. In other words, let us just look at this as 1 plus y dash minus 1 divided by 1 minus y dash. It is very much possible the ones cancel out with respect to each other, and we are left with only y dash. Okay. So, it does not really matter if we lay this out as 1 plus y dash minus 1 in the numerator times dy dash equals dt dash. So, these are now enabling us to actually integrate. So, we could actually try to make two integrals here, dy dash by 1 minus y dash as 1 and minus of integral dy dash equals integral dt dash. In other words, I can easily say that T dash is basically minus y dash minus of natural log of 1 minus y dash plus a constant k, where k is the constant of integration. So, this is an indefinite integral that we are trying to just solve. So, let us now try putting initial conditions to check whether we can find out the value of k. So, let us say at time t equal to 0, the y value was equal to y 0. So, obviously, the t dash, which is actually equal to f square t by lambda, should also be 0 at time t equal to 0, and we can actually write down the value of y dash at time t equal to 0 as the value of y at t equal to 0 per unit y e. Let us call this factor y 0 dash. Okay. So, once we have laid this out, we will have the, if you just substitute the value of t 0, t at 0, and the value of the scaled ratio y dash as y dash 0 in this expression which has been obtained earlier, we have 0 on one side is minus y dash 0 minus ln 1 minus y dash 0 plus k. In other words, k becomes equal to y dash 0 plus ln 1 minus y dash 0. So, if I substitute the value of k back into this indefinite integral, the t dash comes out to be equal to the minus y dash plus y 0 dash. So, I will just substitute y 0 dash earlier. So, y 0 dash minus y dash plus ln of y 0 dash minus 1 divided by y dash minus 1. So, that is how you can estimate the value of t dash, where these are the corresponding gap ratios at time t equal to 0. So, if I wanted to sort of plot the y dash with respect to t dash value, we can see that t dash here is really y 0 dash minus y plus natural log of y 0 dash minus 1 by y dash minus 1. Okay. So, this is y dash, I am sorry. So, if we plot this y dash with respect to t dash, as we can see here, the values of y dash actually changes to 1, okay, unity, because y changes to y e after a long point of time, and so obviously y dash, which is y by y e, should be approaching 1. So, if the t dash, which is actually again f by lambda f square by lambda t, if it is very large value of t, so t dash would go to infinity. So, you can see t dash going to infinity and slowly the y dash approaching 1, the limit 1. Okay. So, it is asymptotic with the line x equal to 1 here in this particular case. So, the figure on this side shows the various values of y dash and t dash, and it is seen that the gap always approaches the equilibrium value irrespective of the initial condition. So, we are deterministically able to say that the final gap that would come out is going to be equilibrium gap through all this mathematical analysis. So, with this I would like to end this module. In the interest of time, in the next module we will take up a little more different topic about tolerances in ECM, and also there are other design parameters related to ECM, like for example the velocity of the flow of electrolyte, which would result in some kind of a design requirement of the strength of the electrode materials which are in place, or things related to surface defects which would come in ECM, etc. But that we will look at in the next module. As of now, I would like to close this particular module. Thank you very much.